It's science, but not as you know it. The Naked Scientists.
Hello, welcome to this week's Naked Scientists, which comes to you from sunny Scotland. I'm Chris Smith, and also here with me is Ben Valsler. Hi, Ben.
Hello.
Now, coming up this week, how scientists are using cloning to create spare parts to repair brains. That's because researchers have tailor-made nerve cells that they can then use to treat mice with a form of Parkinson's disease. Also, we're going to be finding out how a squid's beak has helped scientists to come up with a new way to join different types of materials together. And that could mean things like better bone implants. And we'll also be hearing how researchers have found a way to help people who are suffering from post-traumatic stress disorder. Now, that usually takes the form of rather terrifying flashbacks, which are provoked by harrowing experiences. And we'll be hearing how they found a way to break that cycle. That's all on the way. Ben.
Thanks, Chris. Now, the reason we're in Scotland this week is to take part in the Society for General Microbiology's Edinburgh Conference. So this week's show is all about bacteria. University of Edinburgh researcher Dr. Sarah Staniland will be joining us to explain how some bacteria make miniature magnets inside themselves, and they do that to line up with the Earth's magnetic field, amongst other things. She'll be explaining why they do it and how we can use them to help combat cancer, amongst other stuff. We'll also be talking to infectious disease expert Dr. Clifford Lean about the problem of tuberculosis, which is making a comeback in Britain, as well as hearing how satellites are helping to pinpoint future hotspots for a deadly disease.
Phytoplankton can be monitored using sensors in satellites, so that allows us then to have a global predictive capacity for cholera.
That's Rita Colwell, who will be talking to us later about cholera. Thank you, Ben. Now, also on the way is this week's Question of the Week, where we'll be finding out why people's accents vanish when they sing.
Certainly the opera tradition of singing comes very much from the Italian school of vowels, and singers are encouraged to make their vowels very clean, very Italian-like. Spaghetti.
So the sound of music, but without an accent, and that's coming up shortly. So if you've got a question for us about bugs, bacteria, and some of the diseases that they cause, then do get in touch. Email me, chris@thenakedscientist.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Well, let's kick off with a look at some of this week's hottest science news stories, as we always do. And this particular story, which has been published by Vivian Tabor, and she's a researcher at Sloan Kettering Institute in America. She's found a way of cloning cells from mice so that you can make cells to repair specific parts of the brain, and in this case, repair parts of the brain affected by Parkinson's disease. Now, why this is important is that we think that in diseases like Parkinson's, where the brain loses cells, the only way to make the disease better, or to reverse the signs of the disease, is to put the cells that have been lost back in. But where do you get them from? Well, scientists have done experiments with embryos where you can take embryonic tissue and specifically the bits of an embryo that are going to turn into those bits of the brain that are lost in Parkinson's disease. You can take the individual nerve cells and put them back into the brain and the part of the brain that's lost those cells, and some of them can take root and then they turn into dopamine-producing cells, which you need, and they then pep up the levels of dopamine in the brain and they make the patient's Parkinson's disease get a bit better. Now, the trials that have been done on this have had variable results. In some cases, they've been very good. In other cases, they haven't done very well. And one of the reasons we think for that's happening is because the cells that are being used are not genetically compatible with the patient themselves. So the immune system may move in and destroy those cells, thinking that they're a foreign invader. So how do you get around the problem? Well, that's what these researchers have done. They've said if we can clone an embryo, we make, therefore, cloned tissue which is genetically identical to the donor, then the cells we get from that can be used to just go into the body like spare parts, and they can then be used to repair the damaged bit of the body. So they took mice which had been made to have Parkinson's disease by injecting them with a toxin. They then took some skin cells from the tail of these mice. They took the DNA from those tail cells and injected it into egg cells from a mouse that had already been emptied of their own DNA, and they did some chemical stimulus to those eggs, and that made the eggs begin to divide like an embryo. And the stem cells that were produced were then harvested, and by growing them in a dish with the right growth factors, you can persuade them to turn into brain cells. And they then injected about 100,000 of those brain cells back into the mouse brain, and those animals' Parkinson's disease got dramatically better. But then they did another experiment where they put into those mice cells from another mouse, and in those animals the Parkinson's disease didn't get very much better. And when they looked inside the brains, they found that animals that had had cells that were genetically identical to them, the clone cells, Of the 100,000 they put in, about 20,000 survived. But in mice that received cells from other mice, so they were genetically incompatible, only a few hundred survived. So this shows, for the first time, that you can use cloning technology to make new spare parts for the body, and that there's a definite advantage of doing so.
That's really amazing. And of course, this has been the promise of stem cell therapy ever since it first started, hasn't it? It's a fairly young science, but this is what they've always been aiming for.
It is, and the thing is that it proves and vindicates what scientists have been saying, that this really can bear fruit, this technology. The slight downside is it doesn't get around the ethical implications that you're still creating life, i.e. you're making an embryo which, if it all went according to plan, would turn into a new individual, and you're destroying that to rescue or save life. So it doesn't get around that problem yet, but what it does show is that cloned tissue, which is genetically identical to you, is superior in its ability to repair things like the nervous system compared with tissue which you get from somewhere else.
Well, that's really interesting. But talking about a different type of tissue, and in this case a soft, squidgy one, I've got a question. Do you think you could carve a roast dinner using a knife that had no handle?
Not one that my mother had cooked. Definitely not.
Well, I'd imagine you would probably bleed quite a bit into it, even if it was a particularly good roast dinner, because, of course, you can't hold a sharp thing with soft tissue and expect not to do any damage. But this is actually almost exactly what a squid has to do every time it uses its beak. Now, scientists at the University of California at Santa Barbara have discovered how this sharp, hard beak attaches to the soft, squidgy body, and this leads the way for new materials which can actually perform more than one task, sort of multitasking materials. Now, squid beaks are very, very strong. In fact, the tip of them, called the rostrum, is some of the hardest and stiffest wholly organic materials known. So it doesn't involve any bits of stone or anything, it's just wholly organic, and it's one of the hardest things we know of. It's never been fully understood how this stiff, hard material attaches to the soft material that makes up the rest of a squid's body.
Because you'd think the squid would just change shape when it tried to bite onto something. It would just deform.
Exactly, and you'd think it wouldn't be able to transfer the forces it needs to bite through its prey. But actually, they've found out that the beak can transmit these forces because of the way that it works, in that there's a gradient of chemicals from the soft, squidgy bit to the really hard, sharp tip. Now, Ali Mizerez and his colleagues spotted the clue for this in the colour of the beak, because it fades from almost black at the tip to almost completely transparent where it attaches to the rest of the body. So they took slices through the beak of the Humboldt squid, and they looked at the change in chemicals as you go along the colour gradient. And they found that basically there's a gradient in the amount of water, chitin, which is a bit like keratin, which is the stuff that hair and claws and things is made of, and also proteins that contain something called dopa. So this gradient goes along with the colour. So at the very tip, the sharpest, stiffest bit, there's far more dopamine-containing protein, there's very little water and very little chitin, and the dopa-containing protein makes really strong cross bonds. So this makes it really stiff. And then as you get along, there's more water, more chitin, less protein. So it effectively just has this neat, tidy gradient, allowing the forces to be transferred evenly without there being a point where the beak would break.
Are there any ways in which we could exploit this? Because this sounds like quite a clever strategy to get round an age-old engineering problem.
Well, yes, there are lots of different problems, one of them being muscles sticking to boats. Now, if you could find a way to attach biologically active materials to a solid metal surface, which is in many ways what they're doing here, there are two materials with very different properties, and they're attaching them together, then this would mean that you wouldn't get hull surface fouling. But they could also use it for things like attaching biologically active chemicals to bone transplants, to bone implants, and also things like stents could be able to have extra stuff attached to them just by using this method.
It's amazing what you find when you drill down into nature a bit, isn't it? Well, looking at human behaviour now, and a major problem with humans is that if we're exposed to a very emotional and harrowing experience, then you can lay down a very powerful memory of that experience, and it can then recur and intrude into your consciousness at various times in a sort of flashback. It's almost like a movie playing in front of your eyes of the experience you had, and that's called post-traumatic stress disorder. And it's only a fairly recently recognised phenomenon, but it's very disabling for people that have it, and it's very hard to break the cycle and stop it happening. But now a group of researchers in America, they're Larry Cahill and Michael Alkier at the University of California at Irvine, reckon they might have found a way of doing that. They've been experimenting with an inhalational anaesthetic. So when you go for an operation, one of the ways in which an anaesthetist puts you to sleep is to get you to breathe some gas. And one of the gases they use is sevoflurane. But it turns out that if you give this stuff at a dose about a tenth of that needed to make someone go to sleep, it has effects on the way the brain works, but without altering your consciousness. So they took a group of volunteers, so they had some patients, and they asked them to look at a batch of 36 photographs. And of those 36 photographs, some of them were fairly benign. They were pictures of flowers or a coffee cup or something. And then there were some emotionally distressing or harrowing pictures in the mix too, so severed limbs, someone's arm chopped off or something. And they then asked the patients how many of those pictures could they remember? And of the group who were just asked to do this, they remember 29% of the harrowing pictures and about 12% of the mundane ones. This is a week later. But then they got the same patients and they put them on a low dose of this sevoflurane anaesthetic, about a tenth of the amount needed to send them to sleep, and they did the experiment again. What they found that time was that they remembered only 5% of the harrowing pictures and about 10% of the benign ones. And why they think this is happening is that the sevoflurane seems to interrupt the communication between nerve cells and the part of the brain called the amygdala, which is it's an almond-shaped piece of brain on both sides in your temporal lobe, and that's where the brain concerns itself with processing emotion and distress. And it's connected to the part of the brain called the hippocampus where you lay down fresh memories. And sevoflurane seems to interrupt the connections between those two brain areas. And since the distressing images were the ones that were affected, it makes sense that by breaking that connection with the anaesthetic, you can stop the emotional, distressing experience being patterned on top of the memory. So where they think this might come in handy is if you've got someone who's got post-traumatic stress disorder, by making them relive the memory and then giving them a low dose of this particular agent, you could break the cycle and help them not to get post-traumatic stress disorder in future.
So by repeating it without the harrowing element, you can, in effect, they can learn to not associate this memory with the fear anymore.
They unlearn the emotional distressing part and just remember the memory. So then it breaks that cycle.
OK, well, speaking of memory, it seems that rats are actually even smarter than we thought. They can learn a set of abstract rules and then apply them to a completely new situation, which is actually something that we previously thought only we, a few other primates, and one or two species of bird were actually capable of doing. Now, when a toddler learns to speak and understand language, they don't have to learn every possible word combination. So they don't need to learn the meaning of all these different combinations. What they do is they learn the rules of the language, and they can apply these rules to new words. So the structure of the language is the rule. Now, I'm not suggesting that rats can learn to speak, but they do seem to be capable of the same kind of rule transfer. Now, writing in the journal Science, University College London's Robin Murphy and colleagues conditioned rats to expect food after they were played a certain sequence of tones. Now, there's nothing new there. This is called Pavlovian conditioning, and Pavlov did it with dogs. He rang a bell, then fed them. The dogs then associated the bell with the food, and that's conditioning. But what they did with the rats was give them a sequence of notes, and in this case it was A-B-A or B-A-B. So the sequence of effectively X, Y, X, so note 1, note 2, note 1 again, regardless of what the notes were, was the sequence that meant they get food. If they played a different sequence, so note 1, note 2, or B, B, A, anything like that, they didn't get the food. So they learnt the sequence, not the actual notes.
And did the rats actually perform as expected?
Yes, they did. So they learnt that the sequence that was then associated with food, but the other sequences, when it wasn't the right one, they didn't get food.
And what does this tell us about, A, how the brain works, and B, why is this important?
Well, in this case, it is just normal conditioning. That shows us that rats are capable of learning to associate one external element with a reward like food. But what happened here is they changed the note. And so they gave them the same sequence in a different tone. Now, different tones shouldn't be the same memory kick. So effectively what they showed was they applied the rule of the sequence to a completely different set of environmental conditions, the different tones. And again, they expected food with the right sequence, but not necessarily the right notes. Now, this is part of what we think of as a toolkit to answer all of life's problems and to problem solve. So actually, rats are a lot smarter than we think.
Go rats. This is The Naked Scientist with Chris and Ben. Thank you very much, Ben. And we're talking this week about microbes and bacteria. So if you have any questions for us, you can send those in. The email is open now. It's chris@thenakedscientist.com.
Laying the facts bare. The Naked Scientists.
Now, if you had a choice between a guaranteed reward or taking a risk, which one are you going to go for? Well, most people would choose the guaranteed reward. We all like to play safe. But what about our closest relatives, the great apes? Well, Sarah Heilbronner is a researcher at Duke University in the US, and she's been giving chimps and bonobos, who are an animal related to chimpanzees, a choice between taking a safe bet and being more adventurous. So, hello, Sarah.
Hello.
So, what did you do in your experiments? What did you find?
Right, so we were interested in the evolution of decision-making strategies, and particularly decisions about risk. And as you said, we looked to our closest evolutionary relatives, chimpanzees and bonobos, for help. So the task that we used has a very intuitive human analog, and so I'll describe that first. If I put you on a game show and gave you a choice between what's behind door number 1 and what's behind door number 2, and said that you could keep whatever was behind the door that you chose, and also told you that behind door number 1 there was definitely $40 or 40 pounds, such as it would be.
It's a bit of a low-budget game show then.
Well, I never said it was going to be a very exciting game show, but, you got on it for free, so it should be okay.
And door number 2?
Door number 2, there's a 50% chance that you'll get $10, and there's a 50% chance that you'll get $70. So the expected value of door number 2 is the same as the expected value of door number 1. And as you suggested in your introduction, because you're a human, you're going to prefer door number 1. You're going to prefer the safe bet to the gamble.
Do we know why people tend to be safe bettors, Sarah? Do we have a clue as to why we tend to play safe? Why don't we be more adventurous in our betting?
So this was exactly the type of question we were interested in asking. But instead of asking it about humans, we asked it about chimpanzees and bonobos, these great apes. But, of course, chimpanzees and bonobos don't regularly work with money, nor do they open doors. So we had instead a task where they were choosing between what's underneath bowl number 1 and what's underneath bowl number 2, and we used grapes instead of money. So bowl 1 always covered 4 grapes, bowl 2 50% of the time covered 1 grape, and 50% of the time covered 7 grapes. And what we found was pretty surprising. So chimpanzees, who are our closest relatives, they actually preferred the gamble. They didn't show the same types of preferences as humans, but bonobos were actually very much like humans, and they wanted the safe bet as opposed to the gamble.
So the chimpanzees were always being very adventurous. They were taking the high adrenaline option and gambling, even though sometimes they got much less fruit than if they'd picked the bowl that they knew had just 4 pieces of fruit under it.
Exactly. Now, over time, chimpanzees and bonobos obviously got the same amount of fruit because they were doing these choices over and over again, but they both had these strong but opposite preferences.
Have you any clue as to why, Sarah? Do you know why they were behaving like that?
Exactly. It's a big question. Why? So we went back and did some investigation into what they eat in the wild. Now, we were studying captive chimpanzees and bonobos in a zoo, but if these chimpanzees and bonobos had been in the wild, the chimpanzees would have been facing much more uncertain, much riskier food sources than bonobos. And I'll give you a couple of examples. One is that both of them feed on fruit trees, but the fruit trees that bonobos are feeding on are much more consistent in their environments, and they tend to be larger, so they're a much less risky option. Now, an easier one maybe to understand is that chimpanzees are sort of unique in that they hunt colobus monkeys. So they go out in these big patches, the big groups, and they search for colobus monkeys, and they invest a lot of time and energy into doing this. But if they manage to bring a colobus monkey down, they get a lot of calories. So it's sort of like a high payoff but high loss possibility there.
So what you're saying is because they have a high-risk lifestyle, then evolutionarily speaking, they've grown up to gamble, which is why they do it even when you put them in an experiment.
This is exactly right. So even when they're in an experimental situation and all the conditions are the same, they're still going to maintain the types of preferences that they had back in their evolutionary history.
So coming back to us, humans, for a second, what are the implications for the fact that we are gambling on the stock exchange, we go to the betting, we bet on the boat race? Cambridge lost, unfortunately, this time. It's bad news for us. But are we, therefore, applying the kind of logic that would have guaranteed in our ancestry that we would have filled up the fridge to a modern economy, and therefore there's a flaw in how we process our decisions?
It's a hugely interesting question because, of course, much of behavioral economics over the past few decades has shown that humans are not rational actors, even though we like to think of ourselves as extremely rational and reasoned about our decisions, especially when we're making big decisions about money. But these types of results do suggest that actually we're making decisions at least partially based on what was good for us during our evolutionary history. And the most important thing was not money, because money is a relatively recent invention. The most important thing was food. So these types of results suggest that even for us, even for humans, the rational actor, the Homo economicus, even for us, we're probably making decisions based on strategies that we used in our evolutionary past to get food and that we might not even be aware of now.
OK, well, thank you very much, Sarah, for explaining that to us. So, basically, put simply, next time you choose a safe bet over a risk, you're probably behaving more like a bonobo than a chimp. That was Sarah Hale-Bronner from Duke University. Sarah, thank you.
Thank you.
We've got Kitchen Science coming up in a minute, but before we go there, I have to mention this email we got from Mark in Melbourne, because he's obviously caught the spirit of Kitchen Science. What he wanted to do was measure how fast his sonic toothbrush actually brushes. So he used a sound recorder to measure the sound it makes, and then he looked at the waveform which your computer can show up to see how many oscillations per second. Now, he counted 25 per tenth of a second, which is only 15,000 cycles per minute. But they claim on the packaging that it's 30,000. Now, I'm not really sure. I don't know if this is the best way to measure it. If anybody knows, and do feel free to get in touch. Chris, what do you think?
I think you might be onto something, because when I was driving around in Australia last year, a group of school children decided to measure vitamin C in foodstuffs as their school science project. And they took an off-the-shelf substance, a food, or I should say a drink cordial, which is well-known, very, very powerful brand, which said full of vitamin C. And they thought, well, we'll use that as the control, because we know that will have lots of vitamin C, and if we can detect that, we know our experiment's working. And they kept getting a negative result. And it turned out that the company were lying and saying it's full of vitamin C, and there was none in it. And they had to actually pay a very big fine and then change all their labelling. So it could be that in this particular sonic toothbrush, there's a little bit of adventurous advertising going on. I think if anyone else has a sonic toothbrush and they would like to record it, analyse the waveform, or if in fact you've done this, please do the experiment and then tell us how many cycles a second is it producing. Is there some misleading advertising going on here?
It would be really fascinating to find out. And it is great. We're really pleased, Mark, that you're getting into kitchen science in this sort of way.
Thanks, Ben. Well, still to come on The Naked Scientist, of course, we are talking about microbes this week, and we'll be talking shortly to Sarah Staniland, who is a researcher at Edinburgh University and has discovered some of the micromagnets that bacteria make inside their cells. Why should bacteria make magnets? And moreover, what do these magnets do to the bacteria when they make them? And how could we exploit that technology for bettering human health or staving off human disease? If you want to join us on the programme, send in your questions, comments, thoughts. Email chris@thenakedscientist.com. Now, talking about doing experiments, this week's Kitchen Science is all about microorganisms, and one in particular that most of us have in our kitchens. It's not one that makes us ill so much, although it can do. It's in fact a yeast. We add it to food on purpose to make bread rise and things like that. It's Saccharomyces cerevisiae. It's a tiny organism that actually also makes beer, so it's something we really can't do without. We thought we would do an experiment this week, because it is a microbiology show, on the power of yeast, so finding out how it works and what its role is in baking and beer making. Here's Dave and Ben.
For this week's Kitchen Science, Dave has invited me back to his very own kitchen. Hi, Dave.
Hi there, Ben.
So what do you have for me today?
We're going to be doing an experiment to look at why bread rises.
Lovely. I do like the smell of fresh baked bread, so this will be a good one to know. What do we need if people want to try it out at home?
We want some yeast. You can either use normal yeast, or the special bread maker quick yeast will make it happen a bit quicker. Some warm water, a small lemonade bottle, about half a litre one, sugar and a balloon.
Now, that doesn't sound like we can make bread from that.
We're not actually going to be making bread. We're going to be demonstrating the same thing as makes it rise.
OK, so what do we do first?
First of all, you want to put about a teaspoon of yeast in your bottle.
OK, so if I do that now, what's the next step?
Then you want to put in the sugar, so probably 2 or 3 teaspoons of sugar into the bottle.
Why do we need the sugar?
We're going to be feeding the yeast, and sugar's a really good food.
OK, so let's put a few teaspoons of sugar into this bottle as well. Should that be enough?
That should probably do. It's not really an exact science.
OK, so now we have yeast and sugar in the bottom of the bottle. What else do we need?
Now you want to fill that bottle about halfway up with lukewarm water.
So not kettle water, just sort of hand hot?
Yeah, sort of 30-40 degrees centigrade, that sort of temperature.
OK, so we'll do that now as well. And you only want it half full. We shouldn't fill it to the top.
It should still work if you fill it all the way up, but only doing it half full saves on sugar.
Now I can see that the yeast and the sugar is just settled at the bottom. Do we leave it there, or do we have to stir it up?
You want to stir it up a bit, so give it a nice shake to mix everything up into solution.
OK then. Now I have a sort of yeasty, sugary broth. It looks almost like cloudy lemonade. Is that right?
It isn't cloudy lemonade, but it does definitely have that look, certainly, Ben.
It doesn't smell as appealing as cloudy lemonade, I must admit. So we've now got a yeasty, sugary broth, warm water in a plastic bottle. What do we have to do now?
You want to get a balloon, a fairly large balloon works best, and just stretch it over the lid of the bottle.
OK, so just grab a normal balloon and stretch it across the top. Let me just do that now. OK, so the bottle is now full of yeasty broth and sealed up with a balloon. Now, I can't really see what this has to do with making bread.
I'm going to leave it for about half an hour and see what happens. You might want to keep it warm by putting it in another bowl of warm water.
Or perhaps an airing cupboard.
Yeah, that would work brilliantly too.
OK, well, we will leave our bottle set up. We've put it in a bowl of warm water to keep warm. And then in half an hour we'll come back. If you think you know what will happen to that bottle in that time, then do please let us know. And we'll catch up with you again later on in the show.
Thank you very much to Ben Valsler, who recorded that earlier in the week in Cambridge with Dave Ansell, our very own kitchen naked scientist. Of course, yeast are single-celled microbes. They're a bit similar in the way they work to our own cells, but they're actually members of the fungal kingdom. And they're very interesting. So if you have some yeast at home, you want to do that experiment, do have a go, and then tell us what you find. And anyway, if you don't have time to do it, keep listening and you'll find out what happens later.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
You are listening to The Naked Scientists, and still to come today, we'll be finding out about the new twist in the tale of TB, and that's drug resistance. But now, some bacteria live inside us, some live in freezing cold environments, others at the blistering temperatures near volcanoes or deep-sea vents. But you may not have known that some bacteria actually manufacture their own little magnets. Now, scientists are trying to find out exactly what they use them for, and more importantly, how we can get them to work for us. We're joined by Dr. Sarah Stanaland from Edinburgh University. So, Sarah, tell us about these bacteria.
Yeah, hello, Ben. What they are basically is they're tiny little microbes, about 2 or 3 micrometres long. And they were discovered quite recently, maybe the late 70s, by someone called Richard Blakemore. And he basically discovered them by looking at an environmental sample under the microscope and saw that some bacteria were moving towards a magnet when he put one near it.
It's not an obvious experiment to do, though, Sarah, is it, to put bacteria near a magnet? So that's an amazing intuitive leap, really.
Yeah, it was a very intuitive thing for him to do.
So when you put a magnet near these cultures of bacteria, some of the bacteria or all of the bacteria grow towards the magnet?
Yeah, all the ones with magnets in them will move towards the magnet.
So when you look inside those cells, what's the actual form of the magnet? What is it?
Well, what you see is, as I say, so ones I work with, they come in all different shapes and sizes. So, as I say, they're normally about 2 or 3 microns, but some are round-shaped, some are more rod-shaped. But the ones I work with, they look like wiggly worms. They're like spirals, like a corkscrew. And what you have down the central axis of the cell is you have what looks like a little spine. So you get tiny little electrical nanomagnets. You get tiny little rows, like in a chain, like a string of pearls, if you like.
And what are they made of? What are these nanomagnets?
Well, they're made of either iron oxides, which are magnetite, or the sulfur version of that, where the oxygen is just replaced with sulfur, something called greigite.
So it's very similar to what we think is going on in, say, bats, because they use the Earth's magnetic field to navigate around, and people have now found deposits of this same material in brain cells in things like bats and also fish like salmon that navigate the same way. So,
as well as homing pigeons and people as well.
Yeah, so what do we think they're doing?
Well, there's a lot of conjecture of why they have these magnets, and a lot of ideas come from the fact that the ones found in the northern hemisphere seem to be north-seeking, which if you think of the globe being round and you follow the direction you'd go in if you were going towards the north from the equator, you'd actually sort of swim downwards slightly. So in aligning with the magnetic field, people have proposed that maybe they're using it to swim down because they only grow in microaerobic conditions, which is actually a little bit lower in the sediment. So they're actually using it to find their ideal growth area.
So how would they have evolved some behaviour like that? How would they have got that in the first place? Because it's pretty ingenious.
Yeah, I mean, to be honest, I'm not actually sure about the evolutionary system of how they got it, but I think it was sometimes they spontaneously lose their magnetism, so it could just be a spontaneous.
So if you take north-seeking bacteria to the South Pole, do they die?
No, as I say, when you grow them in the lab, you can put a strong magnet to them, and they just use it to orientate. So it doesn't, as long as you keep them in a microbic condition, they'll grow wherever.
Do we understand the machinery that they use to make these magnets? I guess that's what you're trying to flush out, isn't it?
Well, this is I'd say these have only really been discovered lately in the late 70s, but a lot of the research activity has been based on trying to work out how they do it. Specifically to find out how biomineralisation, which is what the process we call this, occurs. And this has a lot of implications even for humans, because obviously we biomineralise bones. So this has implications in medicine for medical reasons. But humans are very big, complex bodies, whereas microbes are very much more simple. So it's a good model system to start with to look at the biomineralisation process.
So presumably these bacteria have some kind of genetic pathway that enables them to make these magnets. How do they end up with the magnets actually lining up with all their north and south poles in a line rather than just jumbled up? Because if I get some magnetic things and chuck them in a bag, they just form a random jostle of particles. They don't form a nice straight chain.
Yeah, that's a good question. And what people have found is that what they do is they have things called vesicles, which is like a little sac that's attached to the edge of the membrane on the side of the bacteria. And they're actually already formed in that row, but they're held in a row by a protein, a long-actin-like protein that they've just recently discovered. So if you like, that's the string to the chain of pearls, if you like.
How do you think that by borrowing from biology, if we were to nick this from these bacteria that have invented it, how could we use it?
Well, definitely, that's the main key we're looking at of how to use it, because biology is really good at making perfectly formed things. I mean, if you think about it, in our ears we have bones that are extremely delicate and very well defined, and you couldn't get away with having that bone in a crazy random shape. There's not much room for error. So there's the real nice thing about biology is the precision. So we're thinking of using these sort of particles in lots of technological applications, because if you think about it, we use nanomagnets in many applications like recording media, information storage. As you mentioned as well, there's lots of new medical applications for nanomagnets. But the problem is when you synthesize these at room temperature in a lab, then you get a variety of shapes and sizes, and then you have to sort of size select, whereas these bacteria obviously just make them a very much superior defined size and shape.
So you just have to do it the way the bacteria do it, presumably?
Or just get the bacteria to do it for us.
What about in terms of exploiting this for human health and disease? Are there any things that you could use this for? I'm thinking it would be really quite neat if you could have some system where you could tether a drug onto a miniature magnet and then perhaps concentrate the drug in, say, a tumour by using a massive magnet where the tumour is, so all the drug molecules went just there, and then you wouldn't have any side effects around the rest of the body.
Yeah, well, that's exactly what people are working on. I mean, people have used these... The particular reason why the magnetic bacterial magnets are good is because they are surrounded by a lipid membrane. Because they're made in a biological body, they've got this fatty coating, and that's especially good for these sort of technologies that you've just talked about. So because they have this coating, then you can actually genetically engineer the bacteria to have an anchor site, if you like, and that anchor site you can tether a drug to, whereas if it's just an inorganic magnet, then you can't actually just tether a drug that easily to it. So because it has this coating, that makes it ideal for that sort of purpose. So people are looking into drug delivery, but also things like other cancer treatments where you can use a magnet to take the particle to the site of the tumour and then use an alternating field to actually warm up the particle, and then that can either release a drug or actually just burn the cancer site.
Is that coating also the way in which the bacteria detect what north and south is? Because it's all very well having a miniature magnet floating around inside your cell, but how you actually tell the cell what direction your magnet's pointing in must be crucial to sensing the north and south. So is that how they do it? They have some kind of coating that detects the orientation of the particle?
No, the coating, I mean, the particles is very sort of rounded shape, so no, the coating doesn't really do anything to that. The coating is just how... The coating is basically the sac that it's grown in, and it just remains on it once it's grown. So
how does the bacteria tell north and south from the orientation of this thing? Is it physically that the force of the magnetic field twists the bacterium because it's so light? That's
right, yeah. It's not like they have a choice. Even when they're lying, when they've died, even when you look at them under the microscope, you can just switch a magnet like from left to right, and they'll just like rock back and forth. They don't really have a choice in the matter. So attractive even in death. Thank you very much. That's Sarah Stanland. She's a researcher at Edinburgh University. Thank you very much, Sarah.
And now on to a disease that kills thousands of people every year, most of them in the developing world. That's a bacterial infection, cholera, and this causes life-threatening diarrhoea. Most people pick it up by drinking contaminated water because the cholera bacterium usually lives in the intestines of marine creatures like plankton, just like we have bacteria in our intestines. So increases in plankton numbers due to global warming and rising sea temperatures could cause an increase in the number of cholera cases. But watching the plankton also means that scientists now have a way to spot where outbreaks might be about to happen, and they're using satellites to do it. Mira Santhalingham.
We've all heard about climate change in the news. Increasing temperatures, melting glaciers and rising sea levels. But one factor we don't hear much about is the effect climate change can have on human health and pandemics. A bacterial disease now thought to be exacerbated by climate change is cholera, caused by the bacterium Vibrio cholera. One scientist that's been researching cholera is Rita Colwell from the University of Maryland and Johns Hopkins University.
Cholera is caused by a bacterium that is found naturally in the environment of estuaries, coastal waters, lakes, rivers, and even offshore areas. It's associated with plankton, zooplankton. Much like we have in our gut bacteria that help us digest food, so do the zooplankton have in their gut and on the surface of their structures the Vibrio that unfortunately also causes cholera in humans when ingested.
Initially, cholera only affected the Indian subcontinent, but through land and sea trading, it spread worldwide. The main prevention is by filtering and chlorinating water supplies, so this has largely removed the problem in developed countries.
The areas that are affected mostly are the developing countries, India, Bangladesh, Malaysia, countries in the Middle East and Far East, and countries where sanitation, safe drinking water are not available to all. That is the biggest problem, safe drinking water.
So we now know how and where cholera occurs, but how is it possible to look into the future and predict when an outbreak is coming?
The capacity to predict when outbreaks will occur has been made possible by the relationship between the bacterium, the zooplankton species, the copepod, and the phytoplankton, which bloom first, followed by the zooplankton. The phytoplankton can be monitored by chlorophyll measurements using sensors in satellites. So that allows us then to have a global predictive capacity for cholera. And that allows us then to have a head start in knowing when the epidemic will occur. And that then allows us to develop what I call preemptive medicine. That is, to be able to go in with the sufficient vaccine as needed, with warnings, public health measures that can be taken. So that allows us then to preemptively prevent, and that's very important.
It is great to be able to predict and prevent an outbreak, but how far ahead can we realistically predict?
At the present time, the factors that we have been studying, particularly early observations of chlorophyll concentrations that predict subsequent zooplankton blooms, perhaps certainly within 2 to 3 months would allow us a head start in predicting an outbreak.
In its severity, cholera can be fatal, but up to 80% of cases can be treated. The important thing to note about this disease is that it is preventable if known about, mainly through clean water supplies and sanitation. But this isn't always possible in the developing world. So the ability to predict an outbreak and therefore raise community awareness and provide health education in advance could greatly reduce the number of people infected with the disease.
So first, the marine plants bloom, which scientists can see from space. This is followed by a surge in the growth of the plankton which carry cholera, which can then lead to an outbreak of the disease. So by watching what the plankton are doing, you can predict where the disease will strike next. That was Mira Santhalingham talking with cholera researcher Rita Colwell.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
It is The Naked Scientists with Dr. Chris Smith and with Ben Valsler. And tuberculosis is the subject up for examination next, I could say under the microscope. Now, TB has been virtually eradicated from the UK, and a whole generation have had hardly any contact with it. So it's easy for us to forget what a disparaging and serious problem it was in the past, a serious killer disease. But Now we're seeing something of a resurgence, and not just a resurgence of any old TB, but forms of the bacterium which are drug resistant. And Dr. Clifford Lean is a physician in infectious diseases at the Western General Hospital. He's with us. Hello, Clifford.
Hello, Chris.
So tell us about TB. What actually is TB, for a start?
Okay, TB is a disease caused by infection with a bacterium, and that's Mycobacterium tuberculosis. And basically, you get exposed to the germ, and there's a time to delay before your symptoms would appear. So there's a latent period of some sort. And it can affect the lungs primarily, that's what we know mostly, but it can also affect other parts of the body, like the brain, the kidneys, and the gut, and also bone and joints.
Is it true in the case of TB that coughs and sneezes spread diseases? Is that how it gets around?
It certainly does. I mean, it's spread by aerosol route, and those aerosol can float for a bit before people inhale them.
So someone with TB, active open TB, is coughing. You walk into the cloud of droplets they've just coughed out, breathe them in.
Yep.
Then what happens?
Well, the person, therefore, may well be infected, but disease doesn't happen to everyone who inhales this droplet.
Do you clear the bacterium from your body, or does it stay in you?
Some patients can clear it, and others it stays in you and could be dormant for many years, and then reactivates when the immune system gets a bit weaker.
So with age, in other words?
With age, or with intervention by doctors who give immunosuppression to control some of the diseases.
What about lifestyle? What about if someone has a disease that knocks their immune system back a bit, say being alcoholic, or heart disease, kidney disease, or, say, homelessness, just alcoholism or something, or HIV?
Yeah. I mean, you're quite right. All these things tend to make you more likely to get the disease, and I think it's to do with two things. One is exposure, i.e. if you live in a very overcrowded sort of place, you're more likely to be in close contact with people who might pass it on to you. And the other thing is whether or not you're malnourished or you've got a depressed immune system, like being alcoholic, or if you've got HIV.
How do we actually treat TB? Because it's a bacterium, presumably it's just antibiotics.
Yeah. Well, you obviously need to make a diagnosis first. So you hopefully be able to grow the germ, and usually in the UK, we expect to be able to find which antibiotic the bacterium is sensitive to. And usually we use 4 drugs, and the treatment is 4 drugs for the first 2 months, followed by a period of another 4 months with 2 other drugs.
That's a pretty profound regimen. I mean, most bacterial infections, you get antibiotics for 5 days. So why do we need 4 drugs for 6 months in some cases?
That is a very important question, I think, because we have got a lot of bacteria, a big burden of infection, and we've got bacterium who multiply rapidly, and there's a small group of bacterium which grows very slowly, and therefore you can only kill the bacterium when it's growing, and therefore if it's growing very slowly, you need a long time to give the antibiotic to the patient in order to eradicate the infection.
Now, in the last week or so, we've heard of Britain's first case, it's actually here in Scotland, in Glasgow, of a form of TB which doesn't respond to those 4 drugs you mentioned. So where's that come from, and why are we seeing more of this kind of thing?
Okay, I mean, there are 2 types of resistance in TB. One is what we call multi-drug resistance. And the case that you're mentioning is an XDR TB, which is extended resistance in TB. Now, the multi-drug resistant TB has been around for a while. But this XDR TB, which is sort of the very resistant one, there are hardly any antibiotics that is used routinely in TB, which can be used to try and treat that.
Where did it come from? What made it appear in the first place?
Okay, I think resistance is happen gradually over time. We know there's some resistance to some of the 4 components of the drugs that we use, and when people have more resistance, because, as you say, the treatment's very difficult to take. You have to take it on an empty stomach, and you have to take it daily, or at least sort of 3 to 5 times a week, depending on what regimen you use, and for a long period of time.
So you think poor compliance of people, because the drugs are unpleasant and have this rather difficult regimen, people will drop off the wagon for a while. This means that they don't treat the infection properly, and then the bugs learn to become resistant, or you select out resistant bacteria that they're carrying.
Yeah, I mean, that's true. I mean, first of all, you need to make sure, as resistance emerges, that the 4 drugs you're using are the right drugs. So in places like in sort of where it's less sort of resource rich, like in sub-Saharan Africa, there is no sensitive testing. If you use the standard treatment, you're losing some of the drugs if it's resistant already. So, so patients don't take the course of treatment completely. There's recurrence, and there's also likelihood of resistance. Now, if you got resistance already, and then you start getting more resistance when you treat again, then you lose all the drugs that you have against the TB.
Are most of these cases not homegrown? They're imported to this country from other countries?
Exactly. We only have one case in the first one, UK, that came in Scotland. We have had some MDR TB, which is resistant, but not sort of as resistant as the last one. And they've been mostly the XDR has been imported from somewhere else.
So what's the long-term, just to finish up, the long-term sort of prognosis here with TB? Because the numbers look pretty scary. About a third of the world's population are now carrying it.
True, but in terms of the most cases of TB, treatment is very effective if you can make sure that the patient is taking the therapy regularly. And in places where you can't trust patients to adhere to therapy, we've got what we call DOTS, which stands for Directly Observed Therapy. And that's a good way of ensuring that the patient is taking therapy because somebody watches the patient swallow the medication. MDR TB is treatable if we catch it early. XDR TB, very poor prognosis, unfortunately.
Thank you, Clifford. I'll have to finish on that rather worrying note, but thank you for coming in. That's Clifford Lean, who is a physician and an infectious diseases specialist from the Western General Hospital. Thanks, Clifford.
Thank you.
And now it's time to go to Diana O'Carroll with this week's very special Question of the Week.
Hello and welcome to a musical edition of Question of the Week from The Naked Scientist with me, Diana O'Carroll. This time I'll be investigating verbal delivery.
Hi, my name is Archana and I'm calling from North Carolina, USA. My question is about accents. I've noticed that many people, when they speak in a language that is not their native tongue, usually have strong accents. However, when they try to sing a song in the same language, their accents seem to diminish. There are exceptions, of course, but this appears to be generally true no matter what their native language is or what language they try to sing in. Why is that?
Why does our pronunciation change with the addition of music?
I'm David Howard from the University of York, where I work on singing and human voice production. And in answer to the question which relates to accents and what you hear when people sing as opposed to when they speak, I think the answer to this lies in the way that people are trained to sing. We learn vowel sounds, particularly in singing, in a way that allows us to project them to a loud audience. And that normally means that the front of the mouth needs to be more open than it is in speech. So it's a bit like a megaphone. And you articulate the vowels further back. So it opens the front of the mouth up, and the vowels take on a different sound in terms of their timbre, which is really what accent is. And therefore the vowels are being placed in a position for singing, which is not the same as speech. The other way of thinking about it is that certainly the opera tradition, the so-called bel canto tradition of singing, comes very much from the Italian school of vowels, and singers are encouraged to make their vowels very clean, very Italian-like, spaghetti. And when you do that, no matter what language you start in, you will aim towards a vowel which rather removes the accent variation, which in terms of mouth movements is really very small.
We have to change our enunciation if we are to force the sound out in singing, because we have to change the shape of the mouth. Corbell on our forum added that in pop songs it's just been traditional to sing in an American accent since the 1950s, and Ultima emphasised the importance of hitting the notes over enunciation, so it's easier, in karaoke at least, to copy the sounds and the notes than to try and change a variable. Well, to wash all that down, take a listen to our next question.
Hi, I'm Simon from Hiroshima in Japan. The question is in 2 parts. If I'm walking through the desert and I'm slowly becoming dehydrated and I come across a case of wine, obviously with screw caps, and I start drinking it, will it accelerate my dehydration or will it enable me to survive? And would the lower or higher levels of alcohol make a great difference to the situation. Secondly, if the alcohol in wine is potentially harmful to me in a dehydrated state, could I pour it into a bowl and let the alcohol evaporate? And if so, how long would it take to evaporate and reach drinkable levels?
And the following week, we'll be finding out about the action film favourite, An Airtight Room.
Hi, this is Paul calling in from Hong Kong. I tend to drive with all the windows closed and the recirculation function engaged. This way I keep out the diesel fumes and dust. The flip side is I'm breathing in recirculated and progressively stale air. So my question is, if the car were a perfectly sealed container, how big would it have to be for me to survive in it for a day? I'm trying to figure out how long I can drive in a compact car without running the risk of passing out.
Ever been marooned on an island with only a case of wine or trapped in a box? Send your answers and any new posers to questionoftheweek@thenakedscientist.com. Alternatively, have a look at the forum at thenakedscientist.com/forum.
So even when we're singing in our native language, we probably have a very different accent to our spoken voice. There'll be more from Diana in next week's question.
The Naked Scientists. Brought to you by thenakedscientists.com.
And it is The Naked Scientists with Dr. Chris and Ben. And this is The Naked Scientists Kitchen Science, the return. We're going to go back to the kitchen now and find out how Dave and Ben got on with finding out how yeast makes bread rise and how it goes into beer.
Welcome back to Kitchen Science. In case you missed it earlier, what we've set up here is a plastic bottle into which we've put sugar, yeast and warm water, and we've put a balloon across the top. Now, this was about 40 minutes ago, and we've come back now to find that the balloon is starting to inflate, and actually on top of the yeasty broth there's a sort of a layer that looks a bit like the head on a beer. So Dave, what's going on here?
The reason why the balloon is inflating and it's blowing lots of bubbles at the top of the broth is that the broth is giving out a gas called carbon dioxide.
And that's the same gas that we breathe out, isn't it?
Yes, it is. We normally breathe in oxygen and breathe out carbon dioxide. Yeast will normally also do the same thing. It'll breathe in oxygen and breathe out carbon dioxide. But that wouldn't actually increase the volume of gas in the bottle, because for every molecule of oxygen you give out 1 molecule of carbon dioxide, so the amount of gas will stay the same.
So if they were taking in oxygen and giving out CO2, you wouldn't actually inflate the balloon?
No, you'd have exactly the same amount of gas at the end as you started with.
So why has the balloon inflated?
Well, yeast has a neat trick which it uses when there's not much oxygen about. It can burn sugar. Instead of with oxygen to form carbon dioxide, it can burn sugar to form ethanol and carbon dioxide, which gives it the energy to live and grow.
And ethanol is more commonly known as alcohol. So is this how yeast plays a part in the process of making beer?
Yes, it's exactly the same process. When you make beer, you put in a vat of broth with lots of nice sugar in it and some yeast in it. There's not a lot of oxygen there, so the yeast has to burn the sugar to form ethanol and carbon dioxide. The ethanol people drink and seem to enjoy later. And the carbon dioxide can either be just released, or sometimes in some drinks it's kept in there, and so it gets dissolved in the liquid and makes the drink fizzy.
And this is why champagne has its distinctive fizz.
Yes, that's right. They make wine normally the first time round and let the gas escape, but then they add some more yeast and some molasses, which has got lots of sugar in it. Then the yeast ferments inside the bottle, produces lots of carbon dioxide, and so you get all that dissolved carbon dioxide, which makes it fizzy.
So this is how yeast produces lots of carbon dioxide and some alcohol. But we did this in the first place to talk about how yeast helps in bread making. Now, surely yeast doesn't make alcoholic bread?
Well, actually, while the bread is being made, there will definitely be alcohol released, because the yeast does exactly the same thing inside the bread. It breaks down the sugar to form carbon dioxide and ethanol. However, once you cook the bread, you heat it up to very high temperature, and all that ethanol will get boiled off and escape, so the bread actually isn't very alcoholic by the time you actually eat it.
But what about the carbon dioxide? Doesn't that just escape?
Well, the carbon dioxide, it tends to form little bubbles inside the bread. And because dough is quite rubbery, it's got a lot of proteins to make it rubbery, they get trapped inside there, and so the bread expands.
So this is why dough rises?
Yes, just like the balloon on top of the bottle. As the carbon dioxide is released, it takes up more space and makes the bread expand. In fact, sometimes some of the bubbles can expand too much, and you get really holy bread.
It's not very good, is it? How do you avoid having holy bread?
Go through a process called knocking it back, which basically involves hitting it. This tends to burst the biggest bubbles, leaving you with the nice small ones and the nice, much more even-sized foam in your bread.
Well, so it's the yeast that gives us the lovely fluffy bread that we enjoy. But what happens to the yeast when you bake the bread?
Well, after it's done all that lovely work for you, you then heat it up to 200 degrees centigrade, which just kills it.
Oh, that's really sad. Well, do think about that next time you smell some lovely, freshly baked bread. Think of the work that the yeast has put in for you. That's all for Kitchen Science this week. We'll be back with more very soon.
So that's how you make yeast. Well, that's how yeast makes bread rise, and it also puts the distinctive fizz in champagne. Thank you very much to Ben and Dave. Now, it's worth bearing in mind that yeast contributes more than just the ethanol and the CO2 to fermented drinks, because different strains of yeast give subtly different tastes or textures to whatever they're in. So beer used to be made to ferment using yeast that was just found in the environment, but now certain strains have been patented in some cases by companies because they give certain flavours, and a good example of that is Saccharomyces carlsbergensis, which makes a well-known type of beer.
Excellent. Well, we've had a question in for Dr. Clifford Lean here, and this is from Jake in the US. He says he wonders whenever he feels ill, he feels a lot better during the day, and then his symptoms get a lot worse just before he goes to bed. So it feels like he's getting over it, but then at the end of the day he feels ill again. Why does this happen?
Well, when you're ill, your energy levels are probably a bit lower than usual, and in the morning you're fresh. And if you use all the energy before the evening, then you feel tired. But if you pace yourself and do work in small packets over the day, you feel a bit less tired. It's like a battery.
Thanks, Clifford. I've got a question here also for you, Sarah. This is from Richard Hawkins. He's in New Zealand. Says his sense of direction is absolutely appalling. He's wondering about the deposits of iron in the brain, because in the same way as you were saying bacteria make these miniature magnets, we know that other animals, including possibly us, also have them. How do they contribute to us having a sense of direction? How do they work?
Well, there definitely is some research that's definitely true for that in homing pigeons, and it is these particles of magnetite, which is the iron oxide. And we definitely have these nanoparticles of iron oxide in our brains too. So there is compelling evidence to say that they do indeed have a navigational side to them.
Because there have been researchers who've put things like pigeons and bats in magnetic fields and managed to remagnetise their internal compass, so they go off course.
Yeah. That's right.
So if you remagnetise your bacteria, do they go off course?
Yes, they do.
Okay.
And we do have another question here that I can put to you, Clifford, and that is that when you get HIV and AIDS in somebody, say, for example, in Africa, if you then get bitten by a mosquito, can the next person that mosquito bites actually get the disease? Now, we've been asked this by a couple of people, actually this week, one from Riley in Canada and from Jimmy in the UK, so it's obviously a very important question. What do you think?
No. The virus doesn't replicate in the mosquito, and also the inoculum, which is the amount of blood that will be injected or into the next person, is so small that there will be no infection.
So although the mosquito can carry the virus, it doesn't kill it off. The fact that it doesn't breed inside the mosquito means that there's just not enough getting to the next person.
Quite right. Yeah,
but with other diseases like dengue, for example, where it does have the ability to grow in the mosquito, that's why the mosquito is so good at transmitting it, I presume.
Yes.
There's a slightly more trivial, in some respects, question for you, Clifford, which is from George Dowsey, and he says, love your podcast. What is the white stuff that I squeeze out of zits? And is it a bad thing to be doing?
Well, I don't think you should be squeezing the zits. But the white stuff is made up of obviously infections sometimes, or sometimes just secretions from a blocked up sweat glands.
But what are the bugs doing? I mean, are they infecting some kind of gland in the skin? What actually is a zit?
Well, if it's infected, there'll be germs in there, but otherwise it would just be secretions from a blocked sweat gland. Yeah.
So the bottom line is don't squeeze the zit, but if you do, it's just dead debris, bugs, dead skin cells, and secretions.
Yes.
Well, there you have it. Thank you very much. Well, that's pretty much all we've got time for this week, so it remains for me to say a very big thank you to our guests this week, Sarah Stanland and Clifford Lean. They're both from Edinburgh, where we brought this week's show to you from, up here in sunny Scotland, and yes, it has been raining most of the day. Thank you also this week to Sarah Hale-Bronner, who joined us at the beginning to talk about her work on chimps and bonobos, and also to Rita Colwell, who is using satellites to spot where cholera is going to resurge next. Also, a very big thank you to our production team here at The Naked Scientist, to Ben Valsler, who helped this week with presenting the show. Thank you, Ben. And also Diana O'Carroll, Petro Minch, Mira Senthalingam and Dave Ansell. Have a very nice week. Next week, we're science Q&Aing, so if you've got a science question for us, just send it in. Chris@thenakedscientist.com. See you soon. Goodbye.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, Look us up online at nakedscientists.com.